Hello and welcome to the continuation of part 2.1 of the tutorial on writing a Raytracer in Common Lisp. Unfortunately, the last screencast got very long, so I decided to split it in half. Just to recall, what we've done so far was that we adapted the linear algebra package to reflect some minor changes. We've also discussed already the camera and the image plane, as well as the world and view coordinates. We've used ASDF to install ZPNG and also to define interfile dependencies, because we've created a lot of files during the last session, as well as we've begun with the basic implementation of the camera, the scene, and the object superclass. So far so good. What we have yet to do is we have to apply small corrections regarding the camera and the scene. I'm sorry for that, but be sure these are only really basic corrections. After we've done that, we'll finally discuss the intersection of a ray and a sphere, as well as those of a ray and a cube, and hopefully also eventually finish the actual implementation of this tutorials part. However, let's first start out with the small corrections. The first one I just wanted to mention, I already mentioned it last time, but I wanted to point it out once again. Here we are dealing with the inverse of the basis transformation matrix. So I've made a big red arrow here. This -1 was missing the last time. As I said, I mentioned it, but just to be sure, I put it here now. Okay. Now a real arrow. When we talked about the image plane, we also looked very carefully at this angle delta, and I said that delta is just 1/2 of the FOV. However, if we look at our actual implementation, we see that that we've used the whole FOV instead of its half only there. We have to correct for that. Okay, so I would like to just go to Emacs. As you can see, I've already started up Slime, and make first use of ASDF. So make sure ASDF is installed. Yes, it is. Then now we call ASDF OOS. That's a synonym for operate on system. And what we want to do is we want ASDF load op and our package CLRT. That's very nice. You can see everything is loaded and compiled. So now to do the first correction that I mentioned, we have to go to the scene file, and there you can see that delta is p times the ratio of the field of view against 180 degrees. It would work correct if we would write 360 here, so we'll just do it. Then let me get along. We can use, instead of you see where the cursor is, that we are, during every iteration step, we're calculating the x and y coordinates, but instead of using the sum and multiplication, we can do this a little bit easier. The do macro helps us here. We could initialize the y coordinate at max y, during every step decrease the y coordinate by the y step. Here you see that we're not decreasing but increasing it. That was also a slight error. In fact, it's like your image coordinates, your usual coordinates that you are used to, are beginning with 0 and 0 in the upper left corner, and with increasing width and height you come to the lower right corner. However, in our case, yeah, for the image it is correct, but the Raytracer sees the coordinates vice versa. So we have, in order to have a correct image, we have to start out at max y and then decrease it here. Okay, this test is correct. However, here we can use, yeah, our x coordinate always starts at min x, and in contradiction to the max y, here we are just increasing it by step x. Okay, no need for the y coordinate here. The ray, don't know why we have two things here, because it's exactly the same. Must have made a small mistake, so we delete this line. Okay, now this is we terminate as soon as x exceeds the width. This should do, yeah, let's just compile it, Control C, two style warnings. The first one being the variable min_y is defined but never used. That's right, we actually never use it. Yep, let's just remove it, compile once again. And now there's the second one. I bet it's about ray direction. Yep, that's exactly the same. Yeah, so we do not want to delete it. However, right now we don't need it anyway, so we declare to simply ignore it. Control C again, and we've got rid of this error. Okay, then why not head over to the camera, because I'd like to make a few changes here also. Actually, we don't need a accessor function. A reader is sufficient. We make use of clos at this point and define a method. Actually, yeah, basically on top of the v2w matrix reader function method that was implicitly created by the use of the dev class macro. So what we do is we want to define a method here that comes before the method that was implicitly defined by dev class, and our argument here will be the camera. Okay, and we do nothing more than just we check if the slot has already been bound. So unless the slot has already been bound, the slot called w2v matrix, we compute it. This is the code. I can copy the code from here, or actually I cut it here and paste it up there. So here we'll paste it. Correct the indentation a little bit. Okay. So there's another thing. I've checked the cross products once again and found out that this should be vice versa. So the cross product of right and the camera direction should be the cross product of the camera direction and right instead. We just switch it, and I've also looked up the key combination for that. It's Control-T, and it's swapped automatically for us. That's really nice. So that's all we can do for W2V matrix right now. Then actually I think there's no reason for defining world2view as a method. Just a regular function is absolutely enough here. So we have to get rid of the specializers as well. We only stick with cam and back. Don't need to check if the slot has been bound. We just return the multiplication result of W2V matrix of the camera and the vector. Okay. Another reason why I preferred these changes is because now all the code that really regards and also modifies the W2V matrix is now in the, in my opinion, correct method. So everything that's related to the W2V matrix is encapsulated in the corresponding methods, and world2view really does care, only cares about the necessary multiplication now. Let's go ahead, and we also have to export world2view. We haven't done that until now. Just once again compile it. There is no class called cam. Okay, this is from where actually? Let's see where. Okay, this is because it should be dfun. No, this should be dev method. Sorry, but this should be camera instead. Okay, compile it once again. We didn't get any errors this time, so we're also finished with that. And now comes the part just right before we continue with the intersection of ray and a sphere. We should go back once again to our objects file. And the last time we started out, we began writing the finalize method. However, we couldn't do anything here until then because the world2view method was missing. Now we have that world to view, and what we can do now is that we adapt the slot of the object's center. So we set setf slot value of the given object, and the name is center. And what we do is we call world to view with given camera and again slot value. That's it. And for our intersection methods, we'll also need a way to access the center of a object. So we, in this case, let's define a reader for that, and let's call it object center. There's no need actually to export that symbol, as we'll define all those all implementations of any objects within the CLRT objects package. So yeah, we're fine. Just compile it once again, Control C, Control K, maximize the window, and we're done. So I would like to return to the slides, and now we can we can discuss the intersection of a ray and a sphere. That's, as I promised, fairly easy, as if you have a sphere whose center is at the origin of the coordinate system. In a three-dimensional coordinate system, this sphere can be simply described by the equation x squared plus y squared plus z squared minus the radius squared equals 0. Or if, in our case, we prefer a more vector-wise notation, so we write it as the dot product of xyz and xyz once again. Also denote this as x squared, where the x is printed boldly and underlined. So we have x squared minus the radius squared equals 0. Now, as I said, this equation describes a sphere whose center is at the origin. We probably want to have spheres whose centers are not at the origin, so we have to introduce something to some way to translate the center here. We do that by just introducing the vector c, who actually is the center, and replace x with x minus c, I'm sorry. So x minus c squared minus the radius squared equals 0. Now, yeah, that's it so far for the sphere. Now, if we want to talk about the ray, first we have to make sure, or we have to be clear about that every ray, of course, has a origin where the ray starts, and also has a direction. And if you look at this equation, this is pretty clear. So we can describe every point on a ray by the sum of its origin as well as an arbitrary distance, and this distance is t multiplied by the direction, and this is how we can describe an arbitrary point on the ray. We're in the Raytracer actually only interested in positive values, because most of the times negative values would mean that the intersection points that we compute, or the points on the rays that we compute, would be behind the viewer's eye. Nobody can see through the back of its head, so we are only interested in positive values. But anyways, let's move on. If we want to compute the intersection points, we use this RO plus t times RD and replace it with x, so that we end up with this equation here. And then it's just a matter of expanding the equation, the term here, and then factoring out t. We'll end up with this equation. That's pretty basic actually. What we're now interested in is we want to solve actually for t, so we're using the quadratic formula. You can look that up in Wikipedia or wherever you like. I've denoted it here, and also underbraced those parts A, B, and C, which are the cofactors of t, which we're solving for. So yeah, this x12 could also be denoted as t12, like here. So in the end, if we want to solve for t, we just exchange those b, a's, and c's with the a, b's, and c's from up here, and solve the equation. There's only one thing, we'll see that during the implementation. The discriminant of the square root here can be less than 0. If that is the case, there is no intersection between the array and the sphere. We have to check for that. If the discriminant is 0, then there's only exactly one intersection point, or maybe we should say it's not really an intersection point, but at this point this is a tangent point of the array and the sphere. And yeah, for positive values we have two intersection points, one where the array enters the sphere and the other where it leaves again. We do not have to care about the denominator, as our array's directional vector will always be of unit length, so we can be pretty sure that we'll never divide by 0. Okay, let's go back to the source. Don't want to prolong this explanation. Let's start out by writing by opening the file sphere.lisp. Okay, and the first thing, you always want to make sure that you're in the right package. In package CLRT objects, and yeah, why not just define a sphere whose superclass this time is now object. So we inherit all slots and also the initialize instance method from object, which means in turn that we now have a object center. We also have a material. The only thing that we additionally need is the radius of the sphere. Okay, and we also want to provide an init argument for that, call it radius. We want to throw an error if it wasn't provided, because the sphere really needs a radius. So let's say radius must be specified. Okay, and we want it to be of type single float. Yeah, and of course we also want to have a reader sphere radius. That's so far. Now we need to export the symbol as well, export sphere. And why not also update our ASDF system definition in clrt.asd. Now we have, in addition to the other files that we already had, we now also have a file called sphere, which depends on objects. Yeah, and yeah, actually also linalg. I know that linalg is already inherited in objects, but I really want to make sure that all the dependencies are absolutely correct. Now, let me just go back once again to the slides. You can see that we're computing a lot of dot products here. And I think that, of course, we can compute the dot product by using our method m*, but there is maybe a faster way to do it. Let's open linalg Lisp and go to the bottom. If we just make a bit smarter use of reduce and map, actually it's not that smart, but it fits better here. So we define a function called dot a and b. These are our two vectors. Later on we'll also have to check for that. So what we'll do basically is we'll reduce plus, then we'll map. Our result type will be a vector, and our mapping function will be just the product. Our first sequence is matrix data A, the second one is matrix data B. Good. That's it. That's way faster than the iteration here over all the matrix rows and columns. So this of course only works for vectors. So we want to make sure, let's just copy the code from here. This is code for three-dimensional vectors. Copy that, use it, just say is it a vector, and it is if either the matrix columns are 1 or the matrix rows are 1. Okay, so the first thing here is we want to make sure that this that A and B are vectors. Assert is vector A, assert is vector B. Okay. think you get along. So we export the dot product, compile the file, go to the REPL to see if everything works as expected. I don't want to prepend everything with linalg and colon, so I just make use of the linalg package. Now let's go ahead and define ourselves a vector, let's do a or something, make vector 3, data will be 1, 2, 3. And if now we compute the dot product of a and a, it should be like 14. Yep, that's correct. That's 1 squared plus 2 squared plus 3 squared. And thus we can also use the dot product to compute the length of a vector. Now I know we've already written a function for that, but anyways, we have that. Okay, going back to the source, I see that something's underlined here. Yeah, that really should be underlined. We should check that this is equal, or that this is equal actually, and now we're fine. Okay, before we can eventually go to the sphere, we also, we talked about array, so we need an implementation of array. Let's do it. It's fairly easy again. We'll again define a package. I know that I'm defining a lot of packages here. Maybe that's due to my C++ background or whatever. Yeah, I'll just stick with it. I'll do it. And okay, so we need CL and we need linalg, and we are going to create the following symbols. The first one being array, and the second one we want a function called pointOnArray. Then make sure that we're in the package once again. Okay. Now we shouldn't forget about our ASDF definition. We're dependent, our array depends on linalg only. Nice, there we have it. Go back and start out by defining the class array. The array doesn't have really much, but it has an origin and a direction. Now we'll have an init argument for that, and so also again, form will be error, origin must be specified. The type will be matrix. Okay. Yeah, and we need a reader for that array origin. So then go ahead with that direction. That's excellent. Yeah, I can just copy the code. This is exactly the same. Copy it here. Exchange, replace string origin with direction. Now we are fine. That's all that we want to have, but we also have to export the symbols array origin and array direction. Okay. Now the next thing, I really want to make sure that the direction of an array is a unit length vector, so I'll use def method in order to do that. Def method initialize instance, and yeah, instance doesn't matter if we do that before or after. Let's say after. Okay, and we'll specialize on array. So here what we do is basically we compute the length of a vector, and so we assert that yeah, okay, let me go ahead and explain it in a few seconds why I'm doing this assert with less equal. In this case, because we expect unit length vectors anyways, it is sufficient to compute the dot product, and we can just we don't need to compute the square root of the dot product to determine the length, as it should be 1 anyways, and if it isn't, then we already know that it isn't a unit length vector. So compute the dot product of the array's direction and the array's direction. Here another one. Maybe we should give an error message. Direction must be a unit length vector. So what I'm going to do here, due to numerical reasons, it is possible that we end up with ray directions being something with lengths of the ray direction being something like 0.999999998 or something, and this is why we use single float. Let's do a completion here. Single float epsilon. There's a fancy thing that I didn't show you until now. You can use this if you want to do a completion, like, you know, it is something with S and F and E, but I don't know the rest. You hit Ctrl C and meter I. You get a so-called fuzzy completion. You get all these symbols. We're interested in the single float epsilon. Yeah, that's it. Okay, delete the line. Now we're finished with that method that really assures us that we have a unit length ray directional vector. Now the last thing is we want to compute arbitrary points on the array. This is just a convenience function. I'll call it point on array. We get array and a distance, and it's nothing else but the sum of the array's origin plus the result of multiplying the distance by the array direction. Okay, let's go ahead and compile the file. Yep, everything worked out of the box. That's really nice. That's something I love about Lisp. If it works. Okay, I've made enough mistakes to prove the contradiction for that already. So we have our array. I think we've also defined everything here. Now we can go back to the sphere and define our intersects method. Let's go once back, I'm sorry, to the objects file. I have here this intersection of an object and an array. I'd like to add two keywords here. The first one being a lower bound and the next one being a shadow feeler. I'll talk about the shadow feeler when it comes to Blindfong, the Blindfong shading model and lighting. However, we'll make use of the lower bound. The easiest lower bound will always be 0.0. As I said, we don't want to have negative values. However, we also want, due to numerical reasons, once again, to be able to specify a lower bound that's slightly above. So something like this single float epsilon or whatever. And we want the intersects method to return a list of, we want to return a so-called intersection point. I don't want to introduce a class for that because that is really not necessary. We just have to agree that if the intersection testing method completes, it returns a list whose, let's say, first element is the distance from the array's origin to the intersection point, and then the second element is the intersection point itself. And later on we'll also return the normal and texture coordinates there. Okay, go back to the sphere. Now we'll really implement the intersects method, and we specialize it on the sphere this time. We have the keywords. Sorry, also need the array here, which reminds me, let me complete this. We have the key lower bound, initialize it, default value will be 0.0, and we have the shadow feeler, which defaults to nil. We first return t and go back here because, as you see, I'm using the array. Already defined that here, so we have to make use of CRT array as well, and have to update our ASDF definition. So objects now depends on linalg, camera, and also the array. Okay, so we really see that how useful ASDF is for us. go back to the sphere. Now, this is a bit of a tedious calculation now, however we have to do it. We can pre-compute some variables. I'll go back to the slides to show that. We can, as we use it multiple times, pre-compute the dot product of RO and RD. We also, let's use the, I'm sorry, here and here. We can do the same with the dot product of C and RD. We're doing that here and here. And yeah, the dot product of RD and RD, that's RD squared. We use that here and here. So let's go back and say we use RO is the array's origin, RD is the array's direction. Then we said that C is the center of the object, center of the sphere. Then we wanted to pre-compute RORD, let's call it this way, RORD is the dot product of RO and RD. We wanted to pre-compute RD squared, that's RD and RD. Let's go back once again, so we have RORD and RD. We still need C and RD, CRD dot CRD. Okay. Now the first thing that we want to compute is the discriminant, and dependent on the result we decide whether we have only 1, 2 or whatever in the sections. The discriminant will be, let me think, okay, we have, let's just go back once again. The discriminant is this part, so we have 4 times RORD minus CRD squared, so 4 times, what was it again, RORD minus CRD, and that squared, so that's the first part here, and minus the second part, 4 times RD squared, and times the last part here, put that in parentheses again, is RO squared minus R, okay, that's only just once, so dot RO minus 2 times ROC minus 2 times the dot product of RO and C, and then plus C squared. Okay, since we're using the minus here, I might add a minus here as well in order to make that plus. So minus dot C and C, and last also the radius squared minus radius. Okay, that's one hell of an equation. We still need the radius here, sphere, radius, sphere, and I bet it won't work out of the box. Let's just see. Let's print the result. See if it makes any sense. So I'll compile the whole file. There's no class named array. Yeah, that's due to the fact that I should first of all, sorry, a typo here, go to the array, compile that, then we go to the objects. We've added that import of CLRT array, and thus we also have to recompile that. That doesn't designate any package. Why is that? Go back to the array. Yeah, that's completely nonsense. We don't want the package CLRT package, but CLRT array instead. Now we should delete the package CLRT package, get rid of that junk. Compile. Yeah, okay, nice. There it is again. CLRT array. compile it. Now we're fine. We go to objects file once again, compile this. Now the symbol conflict here is clear because of the accidental turning of the symbol. We resolve it in favor of CLRT array, and do the same thing again for the array's origin, and do the same thing again for the array's direction. Now CLRT objects also exports the following symbols. The sphere, yeah, it does, and I'll go back to the sphere, compile that once again. Okay, that's nice. Now, we've already used that package. We'll go ahead and define our first array. So def parameter array, let's call it array, make instance, CLRT array, and its origin will be a vector. Will actually be in the origin, and its direction will be a vector as well, of course, just along the z-axis. Now we have that array. Let's define the sphere, make instance CLRT objects sphere. This center is let's very far away, and we have a radius of 20 or so. Okay, now we've defined that. Now we can use CLRT objects intersects and see if anything works here. Like this, okay, 1600. I know from prior computations that this value is perfectly okay for us for the discriminant. Let's go back to the code here. And now, depending on the discriminant, we decide what we do further. So we say cont, and the first clause will be that the discriminant is less than 0. In this case, we'll return near. Then we want to see if this is exactly 0, and in this case we have only one intersection, and that is -2 times RORD minus CRRD divided by 2 times RD squared. So we have -2 times RORD minus CRD. Yeah, that's something that we're using twice. We may, it could be useful to pre-compute that value. However, let's just finish this first here. So we have this, and we divide it by 2 times RD squared, RD. Yeah, this equation could be shortened a lot. We could remove the 2, for example. Okay, and the other case is where the discriminant is greater than 0. In this case, we have 2 intersection points, and now we have to determine the minimum. So let's say the first point, T1, is yeah, it's actually this value here plus the square root of the discriminant. We can recompute the discriminant in this case. Let's call it root. And this is the square root of the discriminant. We'll use it here. Okay. Two intersection points. The first one, T1, is -2 C. Yeah, that's from above. RORD CRD. And now the whole thing plus, or I could use one row instead, plus the root, and the whole thing divided once again by 2 times RD. And T2 is just the same, the only difference being that here we have a minus. Okay. Now we have that. whatever. Here we have to determine the minimum, and since we are going to, we want the minimum that is still in range, lower bound or shadow feeler maybe, and since we will use similar ranges not only for the sphere but also for other objects, I suggest we write a function for that, call it min in range. We'll have elements and the keywords lower bound, lower bound 0.0 and upper bound. Okay. Good, let's go ahead. The minimum in range, we have a lower bound, we have a upper bound. First of all, we want to get rid of all elements that are outside of the range, and then we want to find the minimum of the remaining elements. So let's say elements is, we can safely use the same name here, or maybe better readable if we use ELTS instead, will be removed if not, and our predicate lambda I will depend on whether we have both lower bound and upper bound or just the lower bound given. We know that we always have a lower bound, so we can just check for the upper bound, and if a upper bound is given, our predicate is that the lower bound is less or equal than I, and that is in turn less or equal than upper bound, or else we just have the lower bound that should be less or equal to I. Okay, so and now, depending on whether there are any elements left, we say when elements, we just apply to minimum the elements. That should do. Let's see, compiled it, but we have two warnings. The first one, the variable elements, is defined but never used. Of course it is not, because I forgot to specify it as a parameter to remove if not. Now if we compile it, we should get no errors. That's correct. Let's go to the REPL. Let's go inside the CRT objects package, and let's see if minimum in range behaves as we expect it to do. So 1, 2, 3, 4. First of all that, okay, we get 1.0, that's nice. Now we define a lower bound, let's say 3.0. Okay, that's exactly it. Yeah, there's no use for the upper bound. We'll just need it for the shadow feeler later on. As I said, I'll cover that particular topic later in the next part of the tutorial. Let's go back to the source. I feel like moving this min in range to the objects file itself. Okay, let's put it here, for example. No need to recompile it since it already lives in the CLRT objects package. Okay, yeah. Instead of exporting a sphere at this point, we could also do it here. Let's try this. Okay, shadows the following symbols. Now that is due to the fact that we accidentally entered those names. So we should unintern them. The first one being Ray from CLRT objects. The next one is Ray direction from CLRT objects. And the last one is Ray origin. Okay, if now I go back and compile, no errors. If I go to the sphere and compile, this cannot work right now. So yeah, let's continue with our minimum in range. Min in, or how did we call it? Was min in range, min in range. elements. This time it's just a list of T1 and T2. Now, yeah, this is what we return. So let's let's bind this to a variable called tmin. And this is really nice about functional programming, that we can just use any expression anywhere, almost anywhere. We can just include it in here. So now we have computed the discriminant. From that point we have computed the minimum intersection. Now we can check. We have 3 cases. This is very easy. We have one intersection. Yeah, we should also use minimum in range, I think, because this makes sure that we are above our lower bound. So we say, if this is the case, return the min in range of a list with only this. And min in range also takes keywords like lower bound and upper bound. Okay, do the same thing here. Keywords lower bound and upper bound. Yeah. Once again, we could, near is as good as an empty list. We can move this once again and say min in range and use the result of this cond, and here we just need to return the list, the correct list. So, and here we again return a list of T1 and T2. We don't need to bind that in that case. We return a list of those 2 values. The first one, this one, and then this one. Okay. And from all that we compute the minimum, lower bound, and upper bound being shadow figure. Okay, now we have to see. Again, it is possible that there is no suitable intersection. So if tmin is set at all, when tmin, then we return something, or else not, but that's implicitly. If we use when, that's implicit. Now we return a list where whose first element is tmin and whose second element is count on ray tmin. Yeah, that's it so far. We also want to let tmin be the first element, that's okay, and let the second element, instead of point on ray, be the object itself, because we really need to track that down also. Yeah, compile it, see if it works, and let's call it. Yeah, before we can do that, we have to go back to the CLRT user package. In package CLRT user. CL user, of course, is the name. CL. Now, here we go. Sorry. Yeah, let's try the intersection once again. Yeah, very nice, 80. Because, as you may remember, matrix print CRT array origin array. The variable is unbound. For some reason I have, maybe I forgot to export that. Ray origin, no. To the REPL. Yeah, this has to be enclosed in parentheses. Okay, so if you recall, The ray's origin was at the origin of the whole coordinate system, thus being at 0, 0, 0. The ray's direction was along the z-axis, and the sphere center was at 0, 0, 100.0, so 100 units along the z-axis in the positive direction, and the sphere's radius was 20, so 80 is just perfect for us. That's exactly what we want. The second argument that we got back was the sphere, and the third and last one, currently the last one, was the intersection point itself. I'd like to inspect this anyways. I'm pretty sure we only have one sphere, so this must be the correct object. But let's go into the sphere and see into the point on the ray and see if it's correct. Yes, it is correct. So our point on ray function works very well as well. Okay, so now we are able to intersect spheres. We might want to go back to our scene file. Now we need something. We need to find the closest intersection, and we need a function called trace ray. Trace ray will going to be recursive in the next part of the tutorial. However, this time it's fairly easy. First of all, let's define find closest intersection. What we want to have is the scene, and we also want to have a ray. We want to enclose that in parentheses, of course, and nothing else. The find closest intersection, yeah, maybe also the lower bound. Okay, let's introduce a keyword for that. That makes it more readable, or just an optional argument. Lower bound 0.0. Let's see. Yeah, we could also do it iteratively, but if we wanted to reduce, yeah, then in this case we'd only we use our own reduce function. We say lambda I and j to be able to compare two objects. So, and lambda I and j, and now since trace ray, the intersection test of the object, as we said, returns the minimum t and as well as some other values in form of a list, and thus we have to deal with this list with its first element. And let's say if the car of I is less than the car of j, then we return I else j. Okay, remember we plan to have a list of intersection points, or maybe the iterative way is even better in this case. Say this will be our overall minimum, or the closest match, and we initialize it with nothing. Let it just be near, and now we iterate over the list or the scene objects of the given scene, and in the end we return the closest match. Now okay, let's see. If we already have a closest match, then first IP will be our intersection point, or make this more verbose. Intersection point is CRT objects. We have used that package, so say intersects, and the current object. What am I doing here? Object on the scene objects. Okay, now it's correct. Intersects, object and the given array, and we provide the lower bound as well. Lower bound. Okay, we'll care about the shadow feeler later. Now we have that intersection point computed, and depending on if we have a closest match already, we have to compare it. So set f closest match to if the car of the intersection point, remember that this is basically Lisp, is less than the car of closest match. In this case, we return the intersection point or else the closest match. And we can even okay, let's do it this way. Sorry for coughing. Set f closest match to the intersection point. Okay, fine. We don't need to export that. However, let's try to compile it. Until now, no errors. At least we don't see any errors. We find the closest intersection in the scene, and yeah, trace ray will make use of that. Define trace ray. Its arguments will also be the scene and the ray, and an optional lower bound. So we can remove that optional here because we always have that lower bound. And in order to make that complete, we also say shadow feeler, find closest intersection, and provide not only the lower bound but also the shadow feeler in this place. And we'll hopefully never have to return to that simple function. However, here we have a optional shadow feeler. Always forget the parentheses today. Okay, so if we get an array to trace, we first have to find the closest intersection, and yeah, the result of trace array will just be the color, a triple, red, green and blue values that we want to set in the image plane at the corresponding point. So we say let closest match be find closest intersection scene ray lower bound shadow feeler. Now depending on whether we have a closest match or not, we return, yeah, since we have no material, it's maybe, and we have no lights actually also, it's sufficient if we just return black or white. So if closest match, then we return let's return a vector. If we have one, let's return white, 55, 55, and if we have nothing, 0, 0, and 0. That's it so far. Now all we have to do is we have to go back to this place here. We set the race direction. Yeah, actually this is not only the race direction but also the coordinate on the image plane. Image plane position. Yep. Okay, we stop here. And what we now do is we say let color be the result of trace ray. We might also, now I also know why I didn't update here, because during every iteration of course we have to do an update. Same thing here. to let the ray start at, yeah, we can make that easier and say, okay, our ray will be, no, I'm very sorry. Let's do it here. So trace ray of make instance crt ray. We'll make a ray whose origin is just the position on the image plane, position, and whose direction is normalized m minus of the image plane position and a 0 vector. We don't need to compute that all over, so we do that here. 0 vector is just a make vector 3. Its data will be make array 3, element type single float, and then we have an initial element of 0.0. That's it. Go back to here, and we always have m minus image plane position is 0 vector and the normalized version of that. So this is where we're tracing the ray, and what we now do, we set the color, aref image data truncate y. Yeah, y, we don't need to truncate that anymore now, since we have converted that back to fixed nums or integers. So y, x, and 0 is the first of the color, then set of aref actually set of can take more of this. yx1 is the second component of the color vector, and then we have yx2, which is the third component of the color vector. Okay, now this finishes the do loop, and this finishes the whole function. Let's compile it. Let's see. Okay, of course we have errors. Invalid number of elements in x0, 1 plus x. Okay. Why is that? This is okay. This is also okay. Here, this should be okay. But let's see. This should also be okay, but we need this. Okay, undefined variable image. Why is that? Really shouldn't be the case. Compile it once again. Unreachable bracket. One too much. Style warnings. But once exactly 4. Variable scene is defined but never used. And what is this? So let's check this from the beginning. This let shouldn't be ended here. This should just end this block. Unbalanced parentheses. So okay, this let here, this parenthesis here, and this here. Then this has it here. That's also okay. This one here. This let has it here. This one there, and then we have one to view. Compile that. Okay, now it worked. I will compile the whole file. Still have undefined function scene. Okay, that's somewhere here. Okay, that's because of this. Compile it, and now we don't have any errors. Okay, what we could try now, we could define a scene, and that parameter scene. What does a scene have? It's an instance of crt scene, and yeah, we also need a camera. Let's do that first. Camera, so an instance of crt camera, and the it has a position. Its position is make vector 3, 0, 0. We need the data keyword 0, 0, 0. It has a up vector, make vector 3, data 0, 0. And it has a look at position, and we want to look at the sphere. Okay, now we have that. Then let's define the scene, get parameter scene, make instance clrt scene, and we have the camera, which is the camera. Oh, and that's it. Okay, now clrt scene, add object, and to our scene we'll add our sphere. Now we can try, let's see, it would be very nice if it worked right now. clrt render our scene width and height, and for test png, let's see where the error is. Okay, invalid number of arguments to the function trace ray. Let's see, trace ray expects scene array, the lower bound and the shadow feeler. Let's see where here we call trace ray and the arguments are, that's really way not enough. So we have a scene, then we also have this, then we have a lower bound and a shadow feeler, and we can leave them as it is right now. Compile this, return. The value is not of type list. This is due to, okay, I have returned a vector, so we have to access this via aref, or let's just make this a list, so everything should be fine. Then direction must be a unit length vector. So let's inspect the camera and see what happened there. Inspect. We inspect the camera object, and then we look at the direction. That is 0, 0, 1.0. So this has happened obviously here when we said that clrt array starts at the image position, and its direction is the normalized m minus the image plane position minus the 0 vector. Let's go to array.lisp and just print ray direction ray direction ray. Compile this. So okay, this is the problem with this. This is the numerical problem. So 1 times the single float epsilon wasn't enough. What we can do is, what can we use? We want to be between 0. Let's make it this way. This is not very accurate, but it should be enough for us. By that. Okay, and he works. At least he works. If we had a percentage output or whatever, we could see how long it takes. Oh, okay, there we are. Let's open the test file and see if we have anything there. Yep, and there's our sphere. That worked almost out of the box. Nice. Okay. Anyways, we have no lighting, we have no material. We're going to cover that during the next time. However, I think that so much time has again passed that maybe we should make another break and then go further and continue with the cube and array and cube intersections. I hope anyways that you enjoyed this part of the tutorial, and I hope I have to apologize for making mistakes, but of course I also make many mistakes. Just this concludes this part of the this sub part of the tutorial. Hope you enjoyed it. Bye.